Okay, today we're going to start exponential functions. It's section 3.1. The generic equation of an exponential function looks like this, where we have f of x, our function is equal to a, this is some constant real number, times b, which is also a constant real number, raised to x. X, our variable, is our exponent. Okay, b is also known as our base. It is not equal to 1. And it's a percent increase or decrease. A is our initial value. So when we get to population problems, and they give us an initial population, that's what we'll plug in for our A. Some examples of exponential functions. Examples are f of x equals 2 raised to the x. Our base 2 is a number, a constant. Our exponent is a variable. G of x is equal to 3 times 1/2 raised to the x. Our a value is a constant. Our b value is a constant. Our exponent's a variable. Here's another example. Our a value is 5, our b value is 4, and our exponent is a negative x. This is okay, it's still an exponential function even though our exponent is negative. Okay, here are some non-examples. Non-examples include k of x, x raised to the second power. The base is a variable, therefore it's not an exponential function. J of x, we have x raised to the square root of 5. The base is a variable, therefore it's not an exponential function. Okay. Next thing we need to talk about is evaluating exponential functions. So here we go, evaluating exponential functions. In your exercises that you'll have to do, the assignment, it's going to give you some functions, and it's going to tell you to evaluate the function for a certain number. So let's evaluate f of x or f of 3 of x, 3 raised to the x for x equals 2. So basically all you're doing is you're plugging in the value they give you for x into the x in the function and finding out what it equals. So 3 raised to the second power is 9. So our function evaluated at 2 is 9. Let's try it with g of x. So this time we have an a value. Our b value is 4 raised to the x. And we're going to evaluate it for x equals 0. So now g of 0, we have 2 times 4 to the 0 power. Anything to the 0 power, if you recall from Algebra 1, is 1. So we have 2 times 1, which gives us 2. Okay, here's another one where we also have an a value. But this time we're going to evaluate it for a negative x. So we'll have a negative exponent. So this time when we plug it in, we have h evaluated at negative 2. We'll have 5 times negative 2. Raised to the negative 2 power, or 2 raised to the negative 2 power. If something is raised to a negative exponent, remember that gives us a fraction. We move this to the denominator, and our exponent becomes positive. So this becomes 5 times 1/2 to the second power, which is 5 times 1/4, which gives us 5/4. Now, let's talk about some more evaluating functions. Here we go. Let's evaluate the function when our exponent is a fraction. Okay, so we have j of x is negative 3 times 4 to the x. We're going to plug in our 1/2. And so now we'll have negative 3 times 4 to the 1/2 power. You recall, the number on the bottom is what root you are taking of this base. So since the 2, we are actually finding the square root of 4. The number on top is the exponent, so this is actually 4 to the first power, which we don't necessarily have to write that 1. So then we actually do some math here. We have negative 3 times the square root of 4, which is negative 3 times 2, which gives us 6. Okay. Now for k of x, we're also going to plug in a fraction, but it's going to be a negative fraction, which adds a little extra that you have to do to the problem. So when we plug this in, we have 4 times 8 to the negative 2 over 3. Again, since it's negative, we have to move this 8 to the denominator, and the exponent becomes positive. But since it is a fraction, we are also taking a root of 8. So it becomes 4 times 1 over, the 3 is on bottom, so we are taking the cube root of 8. There's a 2 on top, so it's 8 to the second power. And when you actually calculate that out, that whole thing becomes 4. So this is actually 4 times 1 over 4, which gives us 1. Okay. Now, we are actually going to figure out our exponential function when we're given a table. Okay, so given a table of values, our x's are negative 2 all the way down to positive 2. And our function gives us 0.1875 at negative 2. At negative 1, we have 0.75. At 0, we have 3. At 1, we have 12. And at 2, we have 48. Okay? In order to find the function, we really want to figure out what the common ratio is here. So if you look, the easiest one to look at is 3 and 12. 3 times 4 obviously is 12. And then 12 times 4 is 48. So then if you check these two, you realize that if I multiply by 4, if I multiply 0.1875 by 4, I get 0.75. Okay, so the common ratio here is 4, and that is actually going to be your b value. So when we are finding our function, we have f of x is equal to a times b raised to the x. Since we know that we're multiplying by 4 every time, we know that our function is going to be a times 4 raised to the x. Now, the simple way of finding your initial value, or your a, is to just go and look at the table and find when your x is 0, what is your function. And in this case, when my x is 0, my function is 3. So if you know what the 0 is, what your 0 value is, then that's your a. So since I know 0 is 3, I know now that my function is 3 times 4 raised to the x. Okay? That's evaluating when you have a table. You are also going to have to evaluate when you're given 2 points. So let's practice doing that. Okay. So here we go. What's going to happen in your assignment today is they're going to give you a graph, and they'll give you 2 points on the graph. And what you guys are going to do is you're going to take each of those points and plug them in to the generic function to solve for a and b. Okay? So I have this written out, but I'm going to write it in another place so that you guys can see it as I go through the steps. Let me put another piece of paper on here. Alright. So, my generic function is f of x is equal to a times b raised to the x. So I'm going to use the this 0 point here, because I know that it's going to give me my a value, but I'll plug it in, and this way you will see how you get the a value. Okay, so 0, 8, this is my x, this is my f of x, So I'm going to replace my x and f of x with those two numbers. So instead of f of x here, I have 8. So equal a times b, and instead of x, I have 0. And remember, anything to the 0 power is actually 1. So 8 is equal to a times 1, so 8 is equal to a. So we have our a value. Now, let's find our b value. And we have to use the other point you're given to find the b value. So, and I'm going to use the fact that I know a is also 8. So, here we go. F of x is equal to, now I'm going to plug in my 8 for my a, times b to the x, and my next point I'm using is -1, 32. So this is my x, this is my f of x, and let's plug those in. We have 32 is equal to 8 times b to the -1. Okay? So 32 is equal to 8 times 1 over b. Because it's a negative exponent, remember that moves it down to the denominator and makes your exponent positive. Okay, so let's times both sides by b to get b out of the denominator. My b's cancel over here, and so I end up with b times 32 is equal to 8. And so I need to divide by 32, both sides. Scooch this up a little bit. Okay. And so 32 is cancelled, b is equal to 1 over 4. So my function for this graph is f of x is equal to 8 times 1/4, let's put it in parentheses, to the x power. Okay? Now, let's talk about the different types of graphs we can get when we have exponential functions. So here we go. We have exponential growth. If it is exponential growth, your graph is going to start low and increase rapidly. Okay? If your graph looks like this, then your b value, your base, is greater than 1. We say the b is a growth factor. An example of this would be f of x is equal to 3 raised to the x. Now, if we're going to describe the end behavior using limits, okay, our end behaviors, this is approaching your x-axis, but will never cross your x-axis, so it's approaching 0. Your x-axis is your asymptote, okay? And this is going to keep growing on to infinity. So if we're going to describe our end behaviors using limit notation or using limits, this is what it looks like. Your limit as x approaches negative infinity is the function f of x equals 0, your x-axis. Okay? And your limit as x approaches positive infinity is f of x equals infinity. Okay. Now, if your b is between 0 and 1, we call this exponential decay. And this is when it's going to start from infinity and approach your x-axis. Okay? Now, it's between 0 and 1. It does not mean that it's negative. It means that your b is a partial, it's a part of a number, it's a fraction. Okay? We call b your base, the decay factor in this type of problem when we have exponential decay. And here's an example. Suppose we have g of x is equal to 1/2 raised to the x power. Okay? It's a decreasing function. And the end behavior, if we're going to describe it using limits, looks like this. Your limit as x approaches negative